Hi, everybody. Today we are going to be talking about Chapter 2, and we're actually talking about the first half of Chapter 2. We're going to cover the part about units and significant figures. Then we will do field notes along with your classmates from practical surveying, and we'll take care of that next week. So the most important thing about this chapter to realize is that surveying is always about measurement. So the numbers that you take down, the numbers that you write down when you survey are all based on real life measurements. That means that including units is an integral part of your answer. So in other words, if you are measuring something in feet, tenths of feet and hundredths of feet, just giving an answer of 100.62 is essentially meaningless because we're only talking about feet. So the answer is always going to be 100.62 feet. Another thing about significant figures or significant digits is significant digits are a way of writing numbers so that they reflect how they've been measured. So in other words, if you use a steel tape that only measures something to 100th of a foot, you cannot report the answer in 10,000ths of feet. Even if you run it through your calculator and you multiply two numbers by each other, it doesn't make any sense to have numbers that are more accurate than the data that you used to create the answer. So those are the things that we're going to talk about today. This is oriented toward math, but really the level of math you need is arithmetic and a little bit of problem solving, not really even any algebra. So having said that, let's take a look at our next slide. This is directly from your textbook. And what this is discussing are the kinds of measurement that we can make in surveying. If you look at the tripod, there's a surveying instrument here at point O, and we are discussing this length, O to A, which is a horizontal distance. This is all illuminated on page 1 of your textbook, just in case you're wondering. But we have horizontal distances, as in O to A. We have O to C, which is a slope distance. In other words, it's measured along the angle. We also have a vertical distance, A to C, of this measurement, and we have then we have some angles. We have angle that starts here on the horizontal and goes upward, and then we have an angle that is in the horizontal plane. We also have an angle that is from E to C. So E is a vertical line that goes straight from the top of, heavenward, so to speak, down to the line that we're measuring. It's called a zenith angle. If we move from the horizontal to our line of measurement, that is called a vertical angle. And in the horizontal plane, in other words, we have to spin this machine and clock it around, that's called a horizontal angle. So those actually six types of measurements. We have a horizontal distance, slope distance, vertical distance, and we have an angle, a horizontal angle, and then we have the fifth would be an angle in the in the vertical plane that can be measured either from vertical when it's called a zenith angle or from horizontal when it's called a vertical angle. This is a very simple representation of a horizontal slope and vertical distance. Now, horizontal and vertical are always going to be perpendicular to each other, so you can use the theorem of Pythagoras here to find one from the other. So if you have a horizontal distance, in this case it's 100, and please note it is not properly unitized. That should be 100.00 feet. That means two different things. One is that it's measured in feet. The other is it's measured in tenths and hundredths of feet. So the two decimal points, 100.00, indicate that you have used an instrument that has the capability of measuring to 100th of a foot. Now, it is incorrect to report it differently. If you wrote that distance as being 100 with no decimal point, that would indicate a much less precise measurement. So in each case, when you write a number, you need to write it as it was measured. V, the vertical distance, is given as 8.0 feet. That means it's only been measured to 1/10 of a foot. The slope distance is 100.32 feet, and that's measured to 1/100th of a foot as well. Now, another thing to notice is that this is ruled by, or you can determine the vertical distance from the slope and horizontal, or horizontal from slope and vertical, and so forth, by using the theorem of Pythagoras. And the theorem of Pythagoras says that if we take the horizontal distance, square it, add it to the squared vertical distance, that it will be the squared of the slope distance. So I would write out, and I'll show this to you briefly, 100 squared, that would be the horizontal distance, plus 8 squared, that would be the vertical distance, should equal 100.32 squared. In other words, or let me write this down, okay, 100.32. So I always abbreviate the theorem of Pythagoras as TOP, just the first letters of the initial, and you can see that I've worked out the math for you. So this would be something that would be a real life surveying calculation. In other words, you can use trigonometry to find other sides or other measurements. You could also find the angle, couldn't you? You could find the angle at the vertex of H and S by using trig. You know, for example, that we have, well, let's just talk about the three main trig relationships. We know that the cosine of any angle is equal to the length of the adjacent side over the hypotenuse, that the sine of any angle is equal to the length of the opposite side over the hypotenuse, and that the tangent of that angle is equal to the opposite over the adjacent. So we could find the angle theta, for example, by saying that it would be the inverse cosine of the side adjacent, which is 100, over the hypotenuse, which is 100.32. And we could do that calculation as well. So that's what that looks like. All right, now I realize that you can stop this. You can just hit the stop button if you need to see that for longer. So I'm not leaving it on the screen for very long. But if you are watching this video, you can just hit the stop button, pause it, and write things down if you need to do so. Right. In your textbook, this is just a little screenshot of page 23. And here we talk about some of the interesting units that we use in the United States. So we know that a foot is equal to 12 inches and that a yard is equal to 3 feet. If we're converting back and forth between the U.S. customary system and the SI system, we find that an inch in the U.S. customary system is equal to 2.54 centimeters. That is based on an international foot. There's a little bit of difference. There's about 6 parts in a million difference between an international foot and a U.S. survey foot. If you look at quadrangle maps, Forest Service maps of any sort, they're all measured in U.S. survey feet, not in international feet. So if you need to convert to international feet, you need to make a correction of about 6 parts per million. And although it's not spelled out here, your authors describe which way that goes, which one is bigger, which one has to be, which way the correction has to go. But it came about because when they were doing surveys, those chains that we talked about, the Gunter's chains, were a little shy, and so if they had that was the data that they had recorded, and so when that turned out to be somewhat shy of an international foot, it ended up that the correction was easier just to make 2 sets of units rather than go back and redo all the maps and plats that by that time had legal basis. So, and we'll talk a lot more about that as time goes on. But for now, just realize that they're not exactly the same thing. The next unit down, we have a rod, a pole, a perch. A rod, pole, perch are the same it's the same physical measurement, 16.5 feet. If you take 16.5 and you multiply it by 4, you find that that number is 66 feet. Now, if you recall, a Gunter's chain is 66 feet long. So when we talk about chaining distances, a rod or a pole or perch is 1/4 of a chain. Another rod that they use in the Southwest United States is a vara, which is about 33 inches. You don't see it too much unless you're working in New Mexico or Arizona, or sometimes in especially Western Texas, you'll see it a little bit. But it's just, you can always find what measurement these equate to in most cases. But I have two that I'll talk about later that are not actually the same all the time. A mile, as we've discussed, is 5,280 feet, is also 80 chains. And then you'll see that a nautical mile, which is what they use for air navigation and sea navigation, is a little bit longer than a nominal or a statute mile. And a statute mile is a regular mile, 5,280, for those of us that are landlocked. Fathom is 6 feet. And so then it talks about a little bit of conversion, which is what we'll do in the last part of this recording, so that you'll have this information to do your homework. Two units that we will not use in this class, but I think they're very interesting, are referred to as, in the Southwest, and a lot in the West, you'll see occasionally something written in terms of smokes, S-M-O-K-E. And then you also have a unit called a sleep. A smoke is the distance that you can see one campfire from another, and so that varies depending on terrain and also some weather conditions and visibility. But they were used a lot. It's a very intangible unit, so they were not really used a lot in official documents, but they were used when people conveyed to each other distances between two different places. The other unit that actually is used up here is called a sleep, and it is the distance that you can travel between the time you wake up in the morning and the time you have to go to bed at night. So in our part of the world, the town 10 Sleep is actually 10 sleeps from the goldfields of southwest Montana along the Bozeman Trail. So if you needed to go to the goldfields of southwest Montana back in the 1800s, and you were at the location that has become 10 Sleep, you knew that it was going to take you 10 more days to get there. So they're a little bit more colorful, but maybe not as, they're certainly not as commonly used or as fixed as the units that we've talked about. The other thing that we need to talk about is significant figures or significant digits, and that means exactly the same thing in my opinion. Now, if you're in a chemistry class or in a science-based class rather than a technology class, there can be some little tweaks to these ideas about significant figures. But in surveying, what we're really talking about is the theory of measurement. And the theory of measurement tells us that we cannot make a number better than the measurement that we took. So if you, like I said earlier, if you measure to tenths of feet, that's all you're going to get in your final product. So if you're measuring a distance and you split it into 3 parts, and you have 3 different people taking these measurements, one of you measures to feet only, one of you measures to tenths of feet, and the other measures to 1/4 of inches. The sum of those 3 distances can really only be reported to feet, because the decimals and the fractions are not relevant to the calculation. If one of you didn't measure to that, then the best you're going to get is the worst piece of data going in. So it's sort of like, you may have heard the expression that a chain is only as strong as its weakest link. Well, that's really true in measurement as well. So significant digits or significant figures attempts to help us report numbers in a way that reflects the way they were measured. So there are some rules on in your textbook about reporting significant figures, and the first thing you have to do is to determine how many significant figures there are in a number. So it's easier for me to tell you what are not significant figures. The only numbers, the only digits that are never ever not significant are zeros. So 1 through 9 are always significant. Zeros are sometimes significant and sometimes not significant. They are significant if they are between, I'm writing this down so I can put it up on the screen again, between two non-zeros, or between a decimal point and a non-zero, or if they are on the far right-hand side of a number. They are not significant, on the right-hand side after a decimal point, because otherwise you shouldn't have put the decimal point there to begin with. Now, they are not significant if they are on the right-hand side with no decimal point in the number, or if they are on the left, whether there is a decimal point or not. And that's because of an idea of scientific notation, that if they're on the left, like if you have a number like 0.00649, I'm going to put this up on the board. Here's the number, here's the rules, here's the numbers. And once again, you can pause this if you need to. Right? The number that I've written there, 0.00649, we have no way to write that unless we use scientific notation without using those zeros, because of the way our number system comes about. So that number actually has 30 significant digits. And as I said before, when I talk about significant digits, I mean exactly the same thing as significant figures. All right, so in your textbook on page 25, there are a series of numbers, and you get to decide how many, or they tell you how many significant figures each of those have. And always remember, every non-zero is significant. So all you're really looking at are the zeros, okay, when you're determining how many significant figures you have. When you add, as I had described earlier, when you add numbers, the answer has to have the same number of decimal places as the least number of decimal places of the numbers in the arithmetic fact. Okay? And then the last thing is, before I'm going to work some problems and show these to you so that you'll have them available, is the idea of rounding numbers. Okay, when you round numbers, what we're really talking is, what if you ran some numbers through your calculator and you got an answer like 175.627 feet, but you only had to report this to the hundredths or to 5 decimal places, or to 5 significant figures. The 7 has to go away. So that means that the 2, it's either going to be reported as 175.62 or 175.63 feet. And the way that you determine that is by looking at the first number that you round off. In this case, it's a 7. It's greater than, it's 5 or greater, so you would round the last digit up. So 175.627 rounded to 2 decimal places or 5 significant digits is 175.63. So I'm putting this up here as well, so you can see that. I'll stop it in a minute as soon as I get it in the right frame. There we go. Okay, so you look at the 7 in the thousandths decimal place when you determine which is going to round. Now, the only question becomes, what if that number is a 5? If that number is a 5, it always rounds up in this class. And this is where, if you're in chemistry or another class, you may have a different answer. Sometimes 5 rounds up, sometimes it stays the same. But in this class, it always rounds up. And the easiest way I can describe that to you is by drawing you this little picture. And you see that 0 through 4, that's 5 digits. 5 through 9, that's 5 digits. So 0 through 4 does not round up. 5 through 9 does round up. Because really what you're implying, if you don't round a 5 up, you're implying that a 0 is exact. And since we are always measuring things, a 0 is no more exact than any other digit. It's just part of the measurement. So something could be 149.9, it could be 150.0, and really 150.0 is not exact. It's also just a measurement, right? So that's kind of how we approach that. I also wanted to take a moment on the page here with the units at the bottom. It talks about a unit of angle being a degree, which is 1/130th, a 1/360th of a circle. Degrees are subdivided into smaller units. A minute is a 60th of a degree, and a second is a 60th of a minute. So you will have numbers written with degrees, minutes, seconds, and we're going to have to convert those as well into decimal degrees or into grads or into radians. I'm going to draw a little pie here. If you have a 360, if you're using degrees, what you find is that every quadrant is 90 degrees. If you're using grads, you find that every quadrant is 100 grads. So in other words, if you look at that paper here, I've just drawn part of the circle, and you can see that that square angle, try and get that in the frame, the square angle can be thought of as being 90 degrees or 100 grads. So the measurement is exactly the same. Now radian is a little bit different. There are 2 pi radians in a circle. Pi is 3.14. So there's only like 6.28 radians, and it's not an exact number. The decimal goes on forever and ever. But that means that 100 grads, or 90 degrees, is pi over 2 radians. And radians is our scientific unit that we use fairly frequently. And they're quite large. So in other words, but that's the conversion between those. All right, so now we're going to work some problems, and your homework for tonight, actually for the coming couple of weeks, is going to be from Chapter 2, problems 2.1 through 2.16. So I'm going to do a selection of these for you, and then I will post them so that you have access to them when you're doing your own homework. All right, so I'm going to start with problem 2.4, and you should follow along in your text. 2.4 says, convert the following distance given in meters to U.S. survey feet. The first number is 4129.574 meters. Each of these problems requires the correct number of significant digits as well. So I need to go back to the page that's still on your screen right here, and I find that it asks me to convert that in survey feet. Okay, so a meter is 39.37 inches. So we use what are called unit conversions, and we say 1 meter is the same as 39.37 inches. And then we see further up north, up above, I mean not really north, that there are 12 inches in 1 foot. So my math problem looks like this. And then I cancel my units. Meters cancel, inches cancel, and I'm left with feet. So I take the numbers 4129.574, multiply that by 39.37, and divide that by 12, and I get, my calculator just waved on me, so I'm just doing it again. 39.37, and then divide that number by 12. And my value is, my calculator says it's 13548.44403. And that would be in feet. However, I have to realize that I have 1, 2, 3, 4, 5, 7 significant figures. So I have to write my answer and is 7 significant figures as well. And so my answer is rounded off to 13,548.44 feet. Okay, so this is part A of problem 2.4 worked out. Okay, continuing downward, problem 2.7, part A, asks me to express 48,983 statute feet squared as acres. All right, so the first thing I need to do is to determine how many square feet there are in an acre. The answer to that, if you look here, an acre contains 43,560 square feet. So 43,560 square feet per 1 acre. Cancel out my square feet, and I take 48,983 and divide it by 43,560. 48,983 divided by 43,560, and the answer is 1.124494949 acres. But once again, I need to go back to my significant figures. See that my data has 5 significant figures. Conversion factors do not affect the number of significant figures of your answer. So I need to write that with 5 significant figures. 1, 2, 3, 4, 5. And it rounds up because the digit I'm rounding on is a 9. So the answer is 1.245 acres. Okay. And that's problem 2.7. Part A. Okay. So to do an angle, I'm going to the angle one is very complicated, and it may take you a little bit of time to figure this out. We may need to work on it in class. But problem 213 says, what are the radian and degree minute second equivalents for the following angles? Part A is 136.0000 grads. Okay. Now, first of all, remember that all of those zeros are going to be significant because there's a decimal place. But I want to convert that first into, let's do radians. We know from the little picture that I drew that pi over 2 radians is the same as 100 grads. So I can use that as my conversion factor. So I write on the bottom 100 grads, and on the top pi over 2 radians. And so I take my number 136.000, divide it by 2, and divide it again by 100, and I get 0.68. The answer is 0.68 pi radians. Now, this looks really strange because it looks like it only has 2 significant figures, but it doesn't, because pi just goes on and on and on forever. So that is an accurate way to write that number. All right, now let's convert it into degree minutes and seconds. We start with the same number, 136.000 grad. Remember that there are 90 degrees per 100 grads, so that's what I'm going to use for my conversion factor. And so I divide by 100, multiply by 90. And that answer is 122.4 degrees. Okay, now when I come out with 122.4 degrees, The 122, the whole number part, is super, but I have to take that 0.4 and convert it into degrees or into minutes and seconds. So I write my answer as 122 degrees. Then I take 0.4, remembering that there's 60 minutes in a degree, so I put on my denominator 1 degree, my numerator 60 minutes, and I cancel degrees, and I get 0.4 times 60, which is 24 minutes. And a minute is abbreviated by a single tick, so I'm going to write that as 24 minutes. Since I don't have a fraction, I don't have to compute seconds because there are no seconds. If that number, instead of being 24, had come out to have a decimal part, I would have to take the decimal part and write it, multiply it by 60 to convert it to seconds. All right. So the last problem that I'd like to do for you today is to take a look at problem 214, which is adding numbers. This gets at the essence of significant figures. This is, and we also have products and quotients. So if you do a product or a quotient, that means multiply or divide, we don't look at decimal places, we look at actual numbers of significant figures. So what that means is that the answer has the same number of significant figures as the smallest number of significant figures of the numbers that went into the product. All right, so I guess I'll actually do two. 214, part A asks me for the sum of 23.15, 0.984, 124, and 12.5. Okay, the first thing I do is I write that out as an arithmetic problem, just a stack, and I add the values together. 23.15 plus 0.984 plus 124 plus 12.5. And the answer that my calculator gives me is 160.634. Okay, now that answer gives you 0 credit in this class because what we're getting at are the significant digits. Since this is an addition, works the same for subtraction problem, we need to look at all of the data that went into that sum and see which has the fewest number of decimal places. That number is 124, which is just accurate to the ones place. It doesn't actually have decimals at all. That means my answer is only accurate to the ones place. So my answer is 160.6, which rounds up to 161. Oh my goodness, there we are. Okay, and last but not least, we'll do a product, which means multiply. 104.56 times 66.8. Get out my calculator. 104.56 times 66.8. And that answer, my calculator tells me, is 6984.608. All right, but we have to look at the significant figures. 104.56 has 5 significant figures. The 0 is significant because it's between 2 non-zeros. The other number, 66.8, only has 3 significant figures. That means my answer only has 3 significant figures. So I actually have to round that off to the tens place. 6984 rounds to 6980 without a decimal place, because that's how you write that number with 3 significant figures. All right, everybody. So that's the lesson for today. You've been told the homework. I will take these pieces of paper, scan them, and load them up to our webpage so that you can see what we worked on today. And if you have any questions, let me know. But this is the lecture for January 18th, so no lecture Thursday. See you later. Have a great day.